and the king, princess that got lost, not the frog, the princess and the king and his rice. So there's a princess. Princess is out. She likes to ride her horse, and she gets lost out in the woods. And the king, it's his only daughter, and he's really distraught. And so he's like, "Somebody help me find my daughter, the princess." And he offers a reward. And so this farmer, he's out in the woods and he's farming. All of a sudden, this princess drives by on her horse. And she decides, so he's like, "Oh, I'm going to take you home." She's lost, so he takes her back to the castle. The king is super, super like happy his princess got saved. So he tells the farmer, "I will give you anything you want as a reward. Like, you just name your reward and I'll give it to you." He doesn't ask for the daughter. So the farmer is like, he's super smart, right? He's like, "Oh, let me think. What do I want? How do I get like value for this thing that I did?" Which wasn't really anything, right? He was just standing around. The princess drove by, but so he knows that the king likes chess, and he says, "I'm going to sort of appeal to the king's sort of gamemanship." He says, "King, this is what I want." He says, "You know what a chessboard looks like? So a chessboard is what, like 64 squares?"
Yeah.
1, 2, 3, 4, 5, 6, 7, 8. One, two, three, 4, 5, 6, 7, 8. Okay, so there's a chessboard. The farmer says, "Mr. King, all I want is I want to play sort of a weird game of chess. I want you to give me 1 grain of rice on day 1 for this first square of the chessboard. Okay? And then the next day, tomorrow, I want you to give me 2 grains of rice. And then the next day, so on day 3, I want you to give me 4 grains of rice. And then on the next day, I want you to give me 8 grains of rice." All right? So he explains this to the king, and the king says, "Farmer, I will definitely do that. You're such an idiot. This is just a few grains of rice. I would have paid you as much gold as you would have asked for. Instead, all you want is some rice." And the farmer says, "Yeah, you would just do this until the end of the board, and then we'll be done, and I'll be considered paid in full." All right? So the king agrees. The farmer goes back, and he takes his first grain of rice for the first day. How does the story end?
Well, it's like a ton of rice.
On about day 20, the king kills the farmer.
Nice. Because he can't pay.
What happens here? Why does, like, down in here, things sort of get out of hand?
On day 20, it's like 400 grains.
So let's figure this out. What is this? This is,
Well, that would be like half-life backwards.
it's sort of like a half-life backwards, right? And instead of exponential decay, it's exponential growth. So if we say this is 2, 4, 8, 16, 32, 64, 128, we're just doubling it every time, right? So this is going to be 2 to the 0, 2 to the 1st, 2 squared, 2 to the 3rd, 2 to the 4th, 2 to the 5th, 6. So this is going to be 2 to the 7th, right? What's this one going to be? 2 to the 8th, 9th, 10th, 11th, 12th, 13th, 14th, 2 to the 15th, right? So after 16 days, it's 2 to the 15th. How many grains of rice is 2 to the 15th?
32,700.
32,700 something, right? So, king's still okay. I gave you 32,000 grains of rice. What's 32,000 grains of rice? That's like a big, like, 50-pound bag of rice, right? So he's like, oh, by here, he gave him 1 bag of rice. King's still kind of okay with this. 2 to the 16th, 17th, 18th. So we've got 2 bags of rice, 4 bags, 8 bags, 16 bags, 32 bags. All of a sudden, this is a wagon load of rice. 2 wagon loads of rice. 4 wagon loads of rice. 8 wagon loads of rice. Right? So this is 2 to the 23rd. So that's about 8 wagon loads. Right? And all of a sudden, he's like, wait a minute. I sent you 7 wagon loads of rice yesterday, and I'm sending you 8. And tomorrow, I'm sending you 16. And then next day, I'm sending you 32 wagon loads of rice. And then 64 wagon loads, and then 128 wagons full of rice. And then all of a sudden, 250 wagons full of rice. And what does the king realize about here?
That he was stupid.
That he ran out of rice, right? He sent 128 wagon loads worth of rice to the farmer who's just trying to collect all this stuff now, and he's selling it and making lots of money. And he's like, wait a minute, 128? How many, like, what would he need if he got to the end? So notice that we're here. This is our 8th square is 2 to the 7th. Our 16th square is 2 to the 15th. So our 64th square is going to be 2 to the 63rd. How much rice would he give him? What's 2 to the 63rd? Bejarano's like, I can't even read the number. What's the number?
9.223372037E18.
E18?
Yeah.
So 9 times 10 to the 18th. What's 10 to the 18th? 10 to the 9th is a billion. So 10 to the 18th is a billion billion.
So a small country with.
So more than a small country, right? So if all we said, like, this was like a wagon load of rice, right? So what's 2 to the 23rd? 2 to the 23rd?
Oh, sorry.
It was 1,000,000,
8,388,608.
So 8 million, 10 million is 10 to the 7th, right? So a wagon load is 10 to the 7th. We have 10 to the 11th, 100 billion wagon loads full of rice.
And
Right?
isn't that on top of the other
And
one
that's
that
just on that day. This is, like, instead of 11 billion, this is 5 billion wagon loads full of rice. And this is 2.5 billion wagon loads of rice, right? So that's just only on one day. So you realize that very quickly this gets out of control. All right? So why do we tell this story? Like, what's the point here?
Don't be stupid. Just ask for some gold because you're gonna get killed. No,
Don't be stupid like the king.
Don't be stupid like the king and agree to this. We're talking about sort of reverse half-lives, right? We're talking about exponential growth. What we're wanting to do when we're thinking about this radiation, we want to start thinking about chain reactions, right? How do we utilize this radiation or this exponential growth in a chain reaction in order to do something? So this is obviously a chain reaction, right? 1 goes to 2, goes to 4, and this is a doubling chain reaction. Why do we call this exponential growth? Yeah, where's the growth? It's up here in the exponent, right? In the 2, the 3, the 4, the 5. It's not geometric growth. What would geometric growth be? It would be like 2 plus 2, 2 plus 2 plus 2. So it would be like 2 times 2, 2 times 3, 2 times 4. That would be arithmetic or geometric growth. And if that was the case, then it would be fine. So this chain reaction growth, this exponential growth, you can see gets out of hand really fast. And in 63 generations, right? So we call each of these squares a growth generation. In 63 generations, you end up with a billion. Right? Happens really, really fast. How does this apply to radiation effects? What we want to do is we want to start looking at nuclear power plants, nuclear weapons, and so we want to understand how that works. How does radiation work in order to use that? So if we look at nuclear bombs, what do nuclear bombs use for fuel? An isotope, yes. Which isotope? Which kind of thing from day one of this class has lots and lots and lots of energy? Right? So uranium, we're going to use an isotope of uranium. So uranium-235. Okay? So uranium-235 is an isotope of uranium.
This is to make a bomb.
So we're going to try to figure out what happens with uranium. What's so special about uranium-235, right? Is uranium-235 radioactive?
Yes. Isn't its nucleus, it's like the particles are super close together so that there's a ton of energy released?
So remember, what is uranium-235? What does a 235 mean? How many protons plus neutrons, right? So it's how many of those little nucleons there are in there, right? So if this uranium-235 nucleus blows up, right? Then there could be lots of stuff flying out, lots of radiation flying out, right? Is uranium-235 naturally radioactive? Is there a chance it's going to blow up? How would we tell if something's going to be pretty radioactive or not very radioactive? What numbers do we use to think about that? Half-life. What do you think the half-life is? So remember when we were talking about PET scans, we're like, oh, if I drink the stuff that's a 20-minute half-life, then it's pretty radioactive, but then it's gone almost instantly, right? So this stuff, what are the chances that this stuff is going to blow up? It turns out that uranium-235 has a half-life of about 700 million years.
That's fast.
Okay, so we should not use that.
So if this was made out of uranium-235, what would it mean?
Still radioactive.
It would take 700 million years for half of it to blow up,
Whoa.
right? Which is a long time. Not very radioactive. There's a very small chance, if I have one uranium atom, there's a 50-50 chance that it's going to blow up in 700 million years. It might last 700 million years without blowing up, or it might not, right? It's 50-50 chance. But that's a long time compared to carbon-14, carbon-14, only 5,000 years. Cesium-137, 30 years, right? So this is a huge amount of time. This is a big half-life. Okay?
So I understand that that is the number of the half-life, but how do we get that?
What do you mean?
How do you get that it's 700 million years?
How do you know that it's 700 million years? You get some uranium-235 and you watch it.
For 700 million years.
Well, yeah, that would be hard.
Yeah.
So let's instead get 700 million uranium-235s and see how many of them blow up. Like, how often do they blow up? And then you can get a rate, right? If you get 700 million of them, right, then maybe one of them is going to blow up in a year. So say, oh, I don't want to wait for a whole year. Let's get 700 billion of them. And then watch, right? So you can then figure out the rates by getting big numbers of them. And if you get like 700 trillion atoms of uranium-235 and they blow up like once every few minutes, then you can sort of calculate out, oh, what's the 50-50 chance for one of those to blow up in a year or in 50 years or 100 years, right? So that's how they calculate these. Okay? So with a long half-life, I get 700 million atoms. Maybe once a year one of them blows up naturally. Is that useful for a bomb? Seems not, right? But one of the nice things about uranium-235 is that I can induce radiation. What does induce mean? Make it happen, right? We induce, where else do we use the word induce? Pregnancies, right? We induce labor, right? Oh, I'm pregnant and I need to have my baby. It's not coming, so let me induce, right? Let me give you some drugs that are going to cause contractions to start and make that happen. So I can induce radioactivity here. I can cause this to be radioactive. And what do? I take a neutron and I shoot it at the uranium-235. And when I shoot a neutron at uranium-235, it fissions. It blows up. And it splits up into a bunch of different stuff.
By shooting a neutron?
Shooting a neutron at it. So shooting a neutron at it does what? Makes it uranium-236, right? I add one neutron. And uranium-236 is completely unstable and blows up immediately.
How do you just like get a neutron? Like just like a neutron by itself?
Yeah.
Just, like figure out how.
You get your neutron gun.
Okay, but how
You
do
could,
just have
you
a
could,
neutron?
so remember that different things are radioactive with different radiation. So carbon-14 is beta radiation. It spits out electrons all the time,
So
right?
you can just collect those electrons?
So if I wanted to shoot electrons at this, I would get some carbon-14 and put it right here. And electrons would just start flying out of it because it's radioactive
so
and
what
spits
has
out electrons. So we would have to find something that has neutrons that are flying out of it.
Okay.
Which I don't know off the top of my head what that particular isotope is, but there's lots of stuff out there that does that.
Is this supposed to have to do with E equals mc squared, or am I just confusing Einstein stuff?
No.
No.
No, I mean, where we've used E equals mc squared, where did we use it? In the PET scan, right?
What?
In the PET scan. What was the PET scan? Positron emission, so a positron and electron Two pieces of mass got together, and what did they do?
Exploded.
They annihilated. They disappeared. How does mass disappear? Turns into energy. E equals mc squared. All of the mass of that electron and proton disappeared and turned into energy. So much mass turned into energy that those gamma rays have lots of energy. So that's where we use E equals mc squared. Right? Anytime you're taking mass and turning it into energy, you're taking energy and turning it into mass. Here, we're not losing any mass. So all of this 235 plus this neutron, right? We have to add up all that mass and figure out how much mass is left over, and it has to be the same, right? We're not losing any mass here, okay? So what happens? We get, like, this 235 breaks up. Maybe 144 of them go this way, right? So there's a big chunk of them. Maybe 89 of them go this way. And there's a whole bunch of, like, gamma radiation that goes all over the place. And the important part of this is that there's two loose neutrons that also get kicked out. Okay?
Oh, and then they just keep exploding.
So this process is called fission. Why is it called fission? Because I took a big nucleus and turned it into two smaller nuclei. So this 144 is probably barium. This 89 is probably krypton, right? So I took this big uranium and I split it up into two smaller atoms, okay? So what's the radiation when uranium-235 blows up? What's the radiation when uranium-235 blows up? All these things. So gamma, you could say gamma is the radiation. Krypton atoms are the radiation. Neutrons are the radiation. Barium is the radiation. More gamma. All of these are the types of radiation that come out. Okay? So this is one fission, and I induced it. I started it. By itself, it's probably not going to happen. But I started that process by shooting a neutron at it. Okay? And you can see where this is going, right? What happens? If I create two neutrons here, then that's kind of cool because if I put another uranium-235 over here and another uranium-235 over here, what's going to happen?
It's gonna keep fission.
This neutron is going to come over here and induce another one and create two more neutrons. And this neutron is going to come over here and induce another one and create two more neutrons and all the other stuff. And then these two neutrons can go hit two more and two more. So I go from one fission to two fissions to four fissions to 8 fissions, right? Just like our Rice King guy, right? We're getting this doubling chain reaction. Okay? Does that make sense how this chain reaction works? So, how is this make a bomb? Or how do we think about a nuclear bomb with this?
Well, is it fission? You said it's like blowing up, so it's like exploding.
So all of this, the gammas, right, and this is like split up, this is energy, right?
Yeah.
So what do I want to do? Like, what do we learn about uranium? We said that this amount of energy is a lot of energy. Remember our original chart?
Yeah.
How much energy was in uranium-235?
Highest one.
Like millions of calories per gram, right? So it turns out that if we look at, if we have enough of these uranium-235s, then it will just keep going 1, 2, 4, 8, 16. If we go up 60, if we have 63 generations, then I'll have the billion sort of explosions going on, right? So this could potentially be releasing lots of energy. How do I make a bomb? How much uranium do I need to make a bomb? If I have 10 kilograms of uranium-235, 10 kilograms, how much energy would get released? 10 kilograms is an important number for nuclear weapons because this is what we would call 10 kilograms of nuclear fuel, we would call a significant amount. Right? And you might think a significant amount, well, why is that special? A significant amount is actually in nuclear weapons proliferation. That's like a technical term. If you have a significant amount of nuclear fuel, that's enough to cause a sustained chain reaction, right? What happens if I only had these 3 uranium-235 atoms. Then I'd induce the fission, some energy would come out, I'd induce more fission, some energy would come out, and these neutrons would fly away. If I only had 3, if there's no more uraniums out here, then I'm done, right?
So you're asking how much?
I'm saying, what does 10 kilograms give me?
Well, you'd have to
There's obviously more than 3 atoms in 10 kilograms. How much energy comes out of 10 kilograms in U-235? So let's just look at that. 10 kilograms is 10,000 grams of uranium-235, right? How many atoms are in 10,000 grams? Do you remember what this 235 refers to? Number of protons and neutrons. What else is it in the periodic table? It's the mole ratio, right?
So it would be 235 times 10.
235 is how many grams per mole, right? So there are 235 grams per 6 times 10 to the 23rd atoms, right? That atomic number is the grams per mole for uranium-235. If it's carbon-14, it would be 14 grams per 6 times 10 to the 23rd atoms, right? So this will tell me how many atoms worth of uranium-235 I have in my 10 kilograms. So what's that number? $60,000 times 10 to the 23rd divided by 235. 2.6 e 25. So 10 to the 25th particles, right? Look up here. What did we end up with here? Only 10 to the 18th, right? In 63 generations. So I can get this doubling way more than 63 generations. It turns out that this is about 84 generations, right? I can get 84 doublings.
What is a generation?
Like from here to here is one generation.
So like a doubling?
A doubling, right? So I can get 84 generations if every atom fissions, right? How much energy comes out of that? Remember on our chart how much energy it had? It was like millions of something, right? It turns out that it is 30 million times TNT, I think. Let me go find my chart. Uranium, 30 million compared to dynamite, right? So per gram, this fissioning process will let out 30 million times more energy than dynamite, okay? So if I have 10 kilograms of uranium, then that's 30 million times 10. That's going to be like 300 million kilograms of dynamite. 300 million kilograms of dynamite is the same as 10 kilograms worth of uranium-235 in terms of energy released. So think about that. What's 10 kilograms of uranium look like? It's like full of this room?
More.
I feel like a kilogram.
Here's 10 kilograms of lead.
Jeez.
And where is lead compared to...
How does he like with the PB? I don't know.
Anybody see lead on there?
PB. Right there.
Oh, 82. So lead is 207, and this is 235. So uranium might be 10 kilograms of uranium might be about this much. Right? Not even the whole thing. So 10 kilograms of uranium. So I get this much uranium-235. Turn it into my bomb, do my fissioning thing, and that's going to be the explosive power of 300 million kilograms of dynamite.
Wait, the explosive.
You could choose. Do I want to drop this bomb, or do I want to drop a bomb that's 300 million kilograms worth of dynamite? They're both going to do the same damage.
But that's radioactive.
But I thought this one was. Because when we're carrying
So
it
it's
on
easy.
our
Obviously, it's
people.
easier for me to carry this. I can just carry this in my backpack or with my handy-dandy rope carrier,
That's
right?
not scary.
Compared to what is 300 million kilograms? Like how much weight can a big airplane carry?
300.
I don't know. Look up the what do we look up? Like load capacity for an airplane
But isn't that the equivalent in energy, not
in energy.
power though? And that's why the only
But-
thing that makes TNT. Like
No, but
80,000 kilograms.
80,000 kilograms. So 300 million kilograms.
way more than a.
So 300 million divided by 80,000 is what?
How many zeros is there? 7.
300 plus 6 more.
Almost 4. It's like 3.6.
300 million divided by 80,000.
Oh, 8.
That's
Oh.
3,700.
So I would have to have 3,700 airplanes completely full of dynamite, right? Almost 4,000 airplanes full of dynamite, and drop all 4,000 airplanes versus full of dynamite, or this much.
That seems a lot easier.
This seems easier, right? This is why the military likes nuclear weapons. Big explosive power in one small package. Now McCreary says, wait a minute, isn't this energy and not power? And aren't we talking about explosive meaning power, like how fast that energy is released? What do you think the power comparison is between dynamite and uranium? Which one can release its energy faster? Or are they about the same?
I think dynamite.
Remember, dynamite's really fast, right? You just light it and it goes, right? So what happens?
Depends on how long that chain reaction.
Depends on how long this takes, right? How long does it take to explode a nucleus, and those guys go out and explode another nucleus
Not
and explode?
long.
It's fast,
Very quick.
right? It's the same speed. So I would say that the rate of these reactions
Around the same.
is around the same. I don't even know which one would be faster or slower, right? So the power is going to be about the same. So if I'm comparing energy, I am comparing the explosive ability of these things. Okay? So it's actually interesting, 300 million kilograms, 4,000 airplanes worth of dynamite compared to that little 10 kilogram brick. All right? Same explosive power, same amount of energy.
Is that why they kind of like stopped using TNT?
Well, I mean, because it just takes so much.
TNT is more of like a firework type of display.
Well, I mean, it was the original dynamite, and so this is how we still compare bombs, right? So now we say, oh, now I'm going to use plastic explosives, or I'm going to use these other chemicals, but we're still saying this is equivalent to dynamite, so we can compare. And what we say is 1,000,000 kilograms, right? So if I say this 1,000,000 kilograms, we would call 1,000,000 kilograms a kiloton, right? So I would rate this bomb as a 300 kiloton equivalent yield, right? 300 kilotons would be the size of that nuclear bomb. I get my 10 kilograms of uranium-235, do all my calculations, say, oh, that's going to be the same as 300 kilotons worth of dynamite. 300,000 tons worth of dynamite, yeah.
So if a uranium, like if 10 grams of uranium is like a third of the lead, then why are bombs so much bigger? Is it just the shell that's?
So we have to think about, like, how do you actually build a bomb, right? So obviously, if I couldn't just take this uranium, why can't I just take, if that was my uranium, could I just take it somewhere and say, here, hold this, and then ignite it? No, I mean, the structure around that, what's the first thing that we have to figure out?
How long it's gonna take for when you light it for it to explode?
Right, and what do we mean by light it?
Like press the button.
When you,
Press the button. I have to somehow figure out, there has to be some device that says, let's throw a neutron at that thing, right? So when I throw a neutron at that,
You don't want to be carrying it.
first of all, I want to throw the neutron, I want it to hit it when I want it to hit it, not accidentally. So I have to shield this thing. I have to make sure that there's no like random neutrons flying around, right? Because what if you're like, oh, I'm carrying my suitcase full of uranium, all of a sudden it blows up because some random cosmic neutron comes flying through, right? So somehow I have to say, I want this to blow up, but I only want it to blow up when I want it to blow up.
So you press the button.
So I have to like protect it, salute, and then when I press the button, somehow that button says, let's throw a neutron at this, and then what else is happening here? Like, is it, yes, go ahead.
Wait, this doesn't have to do with the bomb, but I was just gonna say that isn't it also more dangerous than TNT because the stuff that's produced, the radiation is ionizing and TNT's.
So TNT, so both of these, where's most of the damage done? Knocking over buildings, right? You drop it and it like makes things, there's so much energy, it makes things really, really hot, right? Big wind blows stuff up, it like knocks stuff over. So the explosive power is in the knocking over. That's where the biggest damage is done, all right? But this also has gamma, right? So if you're in that blast radius and you're exposed to these gammas, then maybe there's some biological damage and some radiation exposure that way, right? But like after like the initial blast, all those gammas go through stuff and then it's done. So then what's the other biggest issue here? What else is different? These guys here, we call those fission fragments, right? They're these big chunks of stuff that comes out of fission. These fission fragments themselves are very often radioactive. So then this blows up, knocks over a bunch of buildings, all these gamma rays go through, and this krypton and this barium and all the other stuff, it has to land somewhere. And so where does it land? On the ground, on people.
In the air.
It's in the air, it's floating around, I breathe it in, and then this is also like emitting gamma rays and electrons and alpha particles, and this is also emitting, right? And these things have half-lives of, maybe 5,000 years, 10,000 years, 50 years. It's going to be around for a while. This stuff, these fission fragments that are themselves radioactive, that's what we call nuclear fallout, right? You get that radioactive stuff on dust particles, and then it like floats around and it starts falling down, and you get this radioactive stuff falling down. That's fallout, right? All the excess sort of waste radiation, radioactive stuff falling out of the air, or it could get in the air and sort of go around the globe. So Chernobyl, Fukushima, I mean, even like the nuclear testing we did in the 50s and 60s, that stuff got onto dust particles and it's in the atmosphere. It's still in the atmosphere from the 50s and 60s. So for the last 40, 50 years, it's been floating around. We still have about 1 milligram, right, 0.001 millisievert of exposure every year because of those nuclear tests, right? So it doesn't just disappear right away. Okay.
What about like those people that like bring a backpack into somewhere and it has like bolts and stuff in it? Like, what would that be made out of?
So nuclear, again, who has nuclear weapons and who doesn't?
We have the 9.
The 9 club, the people in the nuclear club, right? The 9 countries. And this is country level stuff, right? So if somebody's got if you're thinking about a terrorist saying they're walking around with a backpack bomb, what are they doing? They're just getting dynamite. So they're just like, oh, I'm going to...
able to get the other stuff.
Well, so this is why we say we have these nuclear non-proliferation treaties, right? It is illegal, with the exception of North Korea, because they haven't signed on, for anybody to buy or sell uranium or the technology or the ideas for how to do this process, right? So our countries have signed these treaties to say we can't sell or buy this stuff to try to prevent this sort of stuff from getting out.
Okay, this is what I don't get. If someone's willing to like use TNT instead, I don't really think they'll care about breaking the law.
Right.
So it's like, why is that?
But I mean, but you could say that about countries, right? So the U.S. signs this nuclear test ban treaty. We're not going to test these weapons anymore, right? So it's illegal for us to do that. What happens if we decide that it's important for us to do that?
You have to tell them.
We're just going to do it, right? I mean, it's like, oh yeah, we're going to sign that treaty until we don't want to. And this is so at the country level politics, what happens? You do that, you sign that treaty, and so this is what's going on with North Korea right now, right? So everybody says we shouldn't be having new nuclear testing. They're doing nuclear testing, so what happens? All the UN now passes sanctions. They say, North Korea, you're not following the rules, right, of nuclear testing, so nobody's allowed to sell you any oil or food. So then they're just like, well, if you either have to make it yourself, or there have to be countries that are willing to break the UN sanctions rule, right? Or you have to just sort of survive and stop. And this is what happened with Iran a few years ago, right? So they were under sanctions for probably 10 years, and it was really bad there. And then eventually that sort of forced them politically into signing a treaty to stop their weapons production. And so now we have an individual treaty
so it
with
took them
Iran.
10 years to realize that maybe we should just stop doing these weapons.
No, it took them 10 years for the sort of the political and social situation in the country to get so bad that the leaders finally were forced into doing that by the people. Right? And usually what happens, like think about what happens in North Korea right now. What's happening if we say don't sell any food or any oil or gasoline or energy?
People start dying.
Yeah, who suffers? The people that are making the decisions?
No.
No. It's the millions of people that don't have food, right? And so then the people that are making the decisions, or like the people in power, are very often saying, oh, we can last another year, right? I've got food. We'll sort of buckle down, and people start dying. And so it becomes sort of a real humanitarian crisis. So you could make an argument. I mean, that would be a really interesting study. What are the actual benefits versus cost to people of political sanctions? Right? Saying, I'm not going to sell food to the country. How often does that actually work? Or how often does that just kill a bunch of innocent people because they have idiot leaders? Right? Yeah.
Well, it's basically like it's a matter of everyone being stubborn, because it's like the 9 countries want to be stubborn and stay firm to their word.
Mhm.
Because if they give in, then North Korea is going to think that they can take advantage of us.
Yeah.
And then North Korea is just like they don't care about their people, and they just care about trying to threaten other countries.
Yeah. It's really complex, right? So how do you have some discourse with a country that's in that situation? Or how do you have discourse when Russia will say, oh, okay, yes, definitely pass those sanctions, but maybe we'll sell you a little bit of food. Like, oh, well, that breaks the whole sanction. That breaks the whole point, right? And so Russia and China right now were sort of in that camp. They're sort of like supporters of North Korea, not because of their weapons, but sort of politically, they're more communist, and so it's like East versus West kind of thing. So there's sort of countries that will sort of back channel food, and then it's like, well, then the sanctions aren't as effective, but they also don't want them to have nuclear weapons. But, I mean, so it's not an easy problem, right? It's complex. Yeah.
When one of these bombs is set off, what causes it to suck in everything around it? Like an atomic bomb?
Does it?
That's very based on here, they just did that. But, like, they showed it where they set it off in an ocean, and it completely sucked in and made a giant hole, and then everything just went.
You saw The American Assassin.
Yeah. I don't know if that's true or not, but.
Did it suck everything in?
Or maybe just push it all out.
So I would say that if there's a bomb underwater, right? That was probably over dramatization, right? But my only guess would be if it's pushing water out of the way underneath, then water has to fall in to fill that gap, make that hole. We can watch. So we're gonna look a little bit at how to actually build these bombs. We're not gonna do a lab, but we'll sort of feed. I know, right? But we'll learn how to build them, and then we'll sort of think about and I've got a couple of videos of actually some of those actual test results from the 50s and 60s of what these things look like, and because there a lot of what happened in that depiction was real, right? Like the mushroom cloud and everything, but that whole big funnel thing, I think was not
Because
They
real.
were talking about it, like, the other characters, they're like, it's gonna suck in everything around it. I don't know if they actually mean suck in or.
Yeah, I mean the only way you could have some sucking is if something else gets displaced, right?
Okay.
Or some cooling, because then you get thermal contraction.
Like a crater?
Like a crater, but it doesn't. I can't imagine unless you displace something,
Yeah.
right? Or you melt something. So underwater, that's kind of weird to me. I mean, you can definitely do that underground. I can melt dirt and it gets smaller, and then it has to cave in. So we'll watch a couple of those next time maybe. Yeah.
If you're not allowed to buy or sell uranium,
Mhm.
does that mean you're allowed to transport it, or is that just people don't transport it because it's the risk of being stolen?
Yeah, I mean so the buy and sell is countries, right? So it's like U.S. can't sell it to Canada, right? So if you can't sell it, but can the U.S. transport it from Washington to California? Sure, right? We can sort of do that within But then there's all the safety issues of how do you do that, right? So let's look at let's look at this. If I said 10 kilograms is a significant amount, would have a 300 kiloton yield. What is that, like a big bomb? I mean, it seems big, right? Compare that to the Hiroshima bomb. So only 2 bombs have been dropped in actual wartime, right? Lots and lots of tests. Hiroshima was a 13 kiloton yield. So we took our 10 kilograms of uranium-235, which is what the Hiroshima bomb was, and it ended up only with 13 kilotons. Remember, a kiloton is 1,000,000 kilograms. So we thought it should be 300, and it ended up being 13. What went wrong? Or why did we not get our theoretical maximum?
Because of all this particles going in the air, like all the what's it called, the fission fragments.
So think about what's happening in this chain reaction, right? So these neutrons come in, fission fragments spread out, these neutrons hit here, those neutrons hit, those neutrons hit. What happens?
It has to stop somewhere.
What happens if one of these neutrons miss? What if this neutron goes like this and it just misses? And then this uranium doesn't blow up, right? The only way we get to this 300 kiloton yield is if we blow up all 10 to the 25th atoms, every single one of them. But sometimes we're going to miss. Sometimes because of this explosive stuff, all these fission fragments, this thing is going to start to blow up. All of a sudden, these uranium might be way over here, right? Neutrons aren't even going to hit it, right? So as it blow up, you have to make sure this process happens fast enough so that as many of those uraniums fission as possible. Okay. So 13 kilotons is what it was. The Nagasaki bomb was different. It was about 20 kilotons. What's the difference between the Hiroshima and the Nagasaki bomb? The Nagasaki bomb didn't use uranium.
What did it use?
It used plutonium. What's the difference between uranium and plutonium? Plutonium that they used was 239.
It's just one more.
It's a few more.
Oh, I thought that was an 8. Sorry.
That's right. It's a few more. The big difference between uranium-235 and plutonium-239, we can induce fission in both of them. I shoot a neutron at uranium, it creates 2 neutrons. I create... That?
Yeah, I thought that was an 8.
That does not look like an 8.
It doesn't look like a 5
No,
either.
I'll grant you that. It doesn't look like a 5, but it doesn't look like an 8. Looks like a 3.
Well, either way.
I give it a 2.
There.
There we go.
Now it looks
That was
less like an 8.
Thank you
Okay.
for that. I really appreciate it.
Plutonium-239, what's the difference?
4.
Plutonium-239, when I shoot a neutron at it, it creates its fission fragments and it creates 3 neutrons
Oh,
extra.
so more explosions.
So I can now go, instead of 1, 2, 4, 8, what do I do?
3, 6, 9. 3,
1,
6, 12.
3,
9,
9,
27.
27, right? Whereas uranium is going to be 1, 2, 4, 8. So what happens? Even after 4 generations, it's a much faster, much more energy is released quicker,
It's like,
right? So it's a tripling chain reaction instead of a doubling chain reaction.
so.
And if the neutrons don't hit them, they have better chances of hitting them?
If there's more neutrons, so there's less likely to miss, right? So there's more likely for this process to happen quickly. So this plutonium bomb is what we did in Nagasaki. That's the one that we dropped. And that one was about a 20 kiloton yield.
How many people died in Nagasaki?
Many.
That's
How many died because of radiation?
Not that many.
Not that many. Remember, the whole purpose of these things is the explosive power.
so
I want to
knock
knock
down
over buildings.
so all these
I want to
people
have the
die.
big fireball. I mean, so it's equivalent to, I want to drop, a few hundred million, a few thousand airplanes worth of dynamite, right? And in fact, I read a while ago, so we've got these bombs, right? And we weren't sure they were going to work. What was sort of the military plan for Japan if we couldn't get these bombs to work?
Then we just kill them all.
They were basically going to carpet bomb those cities anyway.
What does
What does that
carpet
mean?
bomb?
take the 4,000 airplanes, fill them with dynamite, and drop the hundreds of millions worth of dynamite on those places anyway. So they were destroying those cities either way. Do you destroy them with your 4,000 airplanes worth of stuff, or do you destroy them with your 110 kilogram sort of bomb, right? And so effectively, they were destroying the cities. The war was going to be over anyway, but the military decided what?
Let's do it again.
Let's see if we can test this new technology, right?
And I
So
can
let's.
say test, but then kill like.
Well, yeah. I mean, it's like we're killing these people anyway. So do we want to just do it with old technology, or do we want to test this new technology? And so the military tested it, and I don't know if this is true, but I've heard them say that after this Hiroshima bomb, they were ready to surrender, and they're like, oh no, wait, let's drop this one anyway, because it's a different technology. It's using plutonium instead of uranium. We want to make sure that one works too, right? And so we tested one of each.
Was that the last time we dropped a bomb?
That was the first and last time that a bomb has been used, a nuclear bomb has been used in war.
But what's interesting in Chinese historic textbook is that they wanted to drop in Tokyo as well,
Mhm.
but there was like a fog or something above Tokyo, so they couldn't see anything, so they decided to like just drop in Hiroshima and Nagasaki.
Yeah, these were not their first targets,
Yeah,
right?
they were like the first target is Tokyo, but
But yeah, the weather. I think it was the weather that day,
Yeah,
right? It was
the
like and at that time, it wasn't like laser guided bomb dropping, right? It's like you fly a plane over, and there's a guy sitting there like,
No.
there, like drop it, right? He's looking, and if you can't see anything, you don't know. So that's definitely true. That's definitely known that these were secondary targets, right? And so it's crazy. It's like that's what we do.
That's so sad. You're the person. If you're the one who says like drop it, you're the person who is saying to kill that group of people.
But that's not unique to nuclear weapons,
No, I know.
That's
right?
war.
That's war, right? But there actually is a documentary. They interviewed the guys that were in the plane, right? That were actually pulling the trigger, and they like 10 years later or 15 years later, they did an interview, and there's a
Do you
documentary
think they had like PTSD about it?
sort of talking to the, well, yeah. I mean, those guys had like major issues. Like initially, they're like, yeah, we're just doing our duty, and we won the war. But after time, when the reality starts to sink in, right? And again, that's not just nuclear weapons. I mean, a lot of this happens with military veterans. After time, they're like, oh my gosh, what did I get involved with, right? And just sort of that PTSD syndrome happens sometimes years later, right?
If they had, because there's only a 13 kiloton yield, if they had done the TNT, would it have been more destructive?
Yeah, if they had actually got their 4,000 airplanes, it would have been more destructive, right? So this would be equivalent to 400 airplanes full of dynamite.
Which one's more cost effective?
Dynamite or nuclear
I'm
weapons?
assuming it's nuclear weapons, but it's like.
Yeah, I probably just because of just trying to move that many airplanes, right? Like, who owns 4,000 airplanes?
No, that we could just destroy.
Not even like United or Delta or like those. I mean, like those big airplane companies like Southwest or JetBlue, they own a few hundred airplanes if they're the big companies, right? JetBlue probably owns on the order of 100
because
airplanes.
it's like $800 million per year.
Yeah, I mean it's expensive. So if you're talking about like the military owns a bunch of airplanes, but you're talking like actually load up 4,000 of them and have them fly all over the same.
I feel as though the military owns like a ton of stuff and that they don't even use. Like, how many nuclear weapons do we have right now?
How many do we have
Like loads.
in the U.S.?
Not okay. I mean, like that we have like planned that could like or like missiles. Even.
I don't think they would.
So now,
Like we have so many missiles.
right now, the U.S. is right around, I want to say 30,000,
That's what I'm saying.
and Russia is right around 35,000,
And we've used 2.
It's a threat.
But it's
and 30,000, 25,000,
that
where
could
we are
take out
now,
the entire
is
world.
less than half of what we, at the height of the Cold War, we were in the 50, 60,000 warheads. Russia was right around 70,000 warheads, right? That was Cold War buildup. That was like that mutually assured destruction. You have, you can, like with 70,000 warheads, think of what you can do. Drop one of these on 70,000 of the biggest cities in the country, in the world, right? I mean, this is why we said we could actually destroy the world 20 times over.
So we're just like, hey, look at all these weapons I have.
Yeah.
We're like, oh, you've got 20,000, I've got 21,000. Like, oh, well, I've got 22,000 now. Oh, well, I've got 23,000. And this is what that buildup did, right? That's what the Cold War was all about, right? And so now, at the end of the Cold War, we started these START treaties, right? Strategic Arms Reduction. And the START treaties actually were the agreement between Russia and the U.S. to start decreasing nuclear stockpiles. And there's arguments now.
How do you decrease a nuclear? Like, are you just like, oh, this is my missile, I'm gonna go throw it away? Like,
Yeah, effectively, but you recycle, right? Reduce, reuse, recycle. So you have to dismantle that. You say, okay, I've now got all this nuclear fuel. What do I do with it? How do I reprocess it, make it safe? What do I use it for? And make it and a big problem with the fall of the Soviet Union was they started dismantling these things, but then you've got all this uranium, and what happened to it? Well, some of it's in Soviet Union, some of it's in Ukraine, some of it's in Russia, some of it's in Azerbaijan, some of it. Right? All of a sudden, you have like 20 brand new countries that might have access to nuclear weapons because that's where they were stored. It'd be like if the U.S. broke up, and Wyoming now is a nuclear power because they've got a bunch of nuclear weapons in their silos. Iowa, right? Lots of places. Like, so that'd be kind of weird. Like, how do you control all of that? That's a big issue, right? And right now, the U.S. arsenal of like 25, 30,000 weapons is in three categories. There's airplane dropped, submarine launched, and then land launched. Okay, and so they call that the nuclear triad, right? You can launch from the water, from the air, or from land. And there's a lot of argument in sort of U.S. sort of military circles right now. Do we really need the land-based missile
what
launches?
Would that do, the land-based?
So that's like there's a rocket out in a silo,
it's
and
just waiting
and
to
you
go.
and it's just like, oh, here it is, and it's pointing at Moscow, and when somebody pushes the button, it gets launched and goes to Moscow.
Why do they say they don't need that one?
Well, because if you have airplane and submarine, do you really need the land one? And really, in any sort of nuclear attack, first strike sort of thing, the first bombs are all going to, everybody knows where those are, right? Russia knows where they are, China, like everybody knows. So like, if there's any sort of actual war, the first bombs are going to land right on top of those. And so the implication is, if you're going to use them, you have to use them first. Because if you use them second, somebody else is going to blow them up first.
So if
So
we
it
get shot
encourage-
first, it's probably going to land in
so if-
Wyoming. And it's going to like destroy
Yeah,
it.
but what's going to happen is if somebody, and this has almost happened several times, if somebody thinks, oh, Russia launched a bunch of nuclear weapons at us, what are we going to do?
Launch pad.
Before they get here, we're going to launch all of ours, right? And so the fact that it's use them or lose them, the idea is that use them or lose them means that we're more likely to accidentally use them because we need to get them in the air before somebody else lands on top of us. Whereas air-based and water-based, it's not use them or lose them because they can move around and it's hard to target those, right? So there's a lot of argument in the arms reduction community of saying, let's just get rid of those, 10,000 land-based nuclear weapons. We don't need them, and they're not effective, and they're actually more dangerous because they exist. Right? And so that whole arms reduction community there's lots of discussion about what happens. So Russia, U.S., right around 25, 30,000 nuclear weapons. Who's next? Who has the next most?
Wait, say it again. Who was first and second?
Russia, U.S.,
Pakistan.
China. And how many do they have? We've got 30,000-ish.
Like 25,000.
Yeah, 200. Right? So Russia and the U.S., Cold War, massive buildup. All of the other countries, all of the other 7 countries in the nuclear club, right? China, France, England, all in the sort of 200 range. India, Pakistan, all in the like 50s range. North Korea, maybe 20, right? So
Does
like,
anyone only have like one, and they're just like, ooh.
because if you have one, you have 2, because you have to test one. We have like 20,000, 30,000.
Oh my god, that's so much.
So it's so out of proportion to anything else, right? So you're like, what if we cut that in half so we only had 10,000?
What do they do with the other 10,000?
Well, so they dismantle them. They have to repurpose them. They process them, right? And the biggest issue is what do you do with that uranium? Right? You just send it into space, or can we reuse it? What other uses might we have for uranium? Yeah,
Can't
I
go
mean,
too
if the whole
hard.
point of this is to release energy, in this case, it's release energy quickly, right? Bomb. What if I could somehow adjust this so it releases energy slowly, right? If I can release energy slowly and in a controlled way, now I have a power plant. I can release that energy slowly, and I can boil water and make steam and turn a turbine and make electricity. This is what nuclear power plants do. So they just take this same process, but we have to think, I want to do it in a controlled way versus an uncontrolled way. I want not an explosive chain reaction, but a sustained chain reaction. And we'll talk a little bit about how that works probably next time. Okay. So what, are there other chain reactions besides nuclear that you can think of?
That thing on your computer.
Oh, is that a chain reaction? How so? When I talk about chain reaction, what's happening here? Are there other exponential chain reactions? That would be a 1 to 1 to 1 to 1 to 1, right?
When you bowl.
When you
hit
bowl,
the first one, and then the next one.
you hit the first one hit, like you hit exactly on that, right? First one hits the second two, and then the fourth, right? And that's a very short chain reaction.
Like 100 pin bowling.
What is it? Dominoes. If you set up like a domino chain reaction, right? Anything else that's not contrived,
What's contrived?
like made up, like you set up. Anything else in nature?
Oh, like animals when they
Something
eat
that we've
each
talked
other.
about yesterday for a long time.
Isn't a fire?
Cancer. Cancer is an exponential chain reaction, right? One cell creates 2, creates 4, creates 8. So all of a sudden you have a tumor. So there's a chain reaction, right? And so what do we want to do with cancer? Effectively, we want to try to block these neutrons, right? We want to try to block one going to the next. So if I can cause one cell to not divide, right, then I'm helping to slow the cancer rate. So I want to try to moderate that chain reaction. What about a fetus?
Oh, fetuses.
Is that a chain reaction?
Yeah.
Exponential?
Yeah, it would be.
Is it? One cell, you start with one cell, and then it divides to 2, and then it divides to, each of those 2 divides, so you have 4, and then every cell divides, so you have 8, and then you have 16. Is it exponential for the entire 9 months? What would happen? Imagine, I mean,
It
just
would be
think about
like a mega
So,
large baby.
Well,
inside
and let's
you.
think about what happens. What it, like, let's say your due date is tomorrow. Okay, so your baby
So
is,
it'll double
you've
by
got an
today.
8-pound baby in you, right?
16 pounds.
And then you're like 1 day late, 16-pound baby. 2 days late, 32-pound baby.
It stops.
So it's not exponential at the end, but it is exponential at the beginning. So somewhere along the way, your body decides, I'm going to moderate that exponential growth, right? Same thing, if I cut my skin, I'm going to get exponential growth while it heals, and then it stops being exponential. So the body's pretty amazing in the fact that it can manage that exponentialness, right? It can say, oh, this is when I need exponential, this is when I don't need exponential. You don't like that word? Exponentialness? Okay, yeah.
I don't want to ask.
Okay. Fetus, cancer. What else? Any other chain reactions you know of? Common cold. How so?
You sneeze
I
on
have
someone
cold
else.
and I can give it to Allie and then Allie can give it to someone else.
Okay, so if you, yeah, like Riley has a cold and then she sneezes and then 2 of her best friends get colds. And then
They sneeze.
those 2 of their friends go sneeze on their other friends and then 4 people have a cold, right? How long would it take if Riley is sick and we had exponential growth for everybody on campus to get
Not
a
long.
cold? How many generations? How many sneezes would it take?
Like 60.
We do what?
8 to 9.
1, 2, 4,
It
8.
depends if you count faculty or not.
Okay.
It'd be 8 to 9.
So 8 or 9 generations, and all 400 or 500 people on campus would, right? So only 8 sequences of sneezes, and everybody's sick. It's an epidemic, right? So when you're talking about something like Ebola or SARS or some of these very contagious diseases, right? Exponential growth is a real problem. How do you fix that? What do we advise you to do if
Go
you're sick?
home.
Go home. Quarantine yourself.
Take
What does
some
quarantining do?
Isolate.
Right? It says, let's put you in a box so that your contagion, these neutrons in the uranium case, can't actually go and hit somebody else. right? I want to isolate that. I want to stop that chain reaction, right? So any sort of virus or viral infection or disease could be a chain reaction, but also other viruses, right? Like computer viruses. It's an exponential chain reaction. You get a computer virus, and what does it do? It downloads your contacts and emails that virus to everybody in your contact list, and then it grabs all their contacts and emails it to all of their contacts. So is that a doubling chain reaction? No. It doesn't only email 2 of your friends.
Oh, because they
Like, what if you have 100 friends in your contact list?
Who has 100 friends? Just kidding.
Okay, so if you have 3 friends, right? If you have that many contacts, it could go 1 to 100 to 10,000 to and then all of a sudden, how long does it take for the entire world to be infected? Right? If it's a 10 or instead of doubling or tripling, it could be 10, 10, 10, 10. If it's 10, it only takes 9 generations for the entire world, right? 10 to the 9th is a billion. So it takes only 9 generations for the entire world to be infected. And again, how do you fix that? You quarantine, right? You unplug your computer, you turn it off, you you disconnect from the internet so you can't send emails. Okay. Make sense? All right, so next time I think what we'll do is we'll actually talk about the technology for how to build these bombs and nuclear power plants and just try to see see if we can understand a little bit better what's going on in North Korea and Iran and what the U.S. sort of procedure on that will be and whether we should worry about that or not. Okay? All right, so you have your